Today we're going to talk about algorithms for reinforcement learning that actually directly learn value functions or Q functions without explicitly representing policies. So before we start on that, a few logistical notes. Homework 2 is due in 1 week, so hopefully all of you have started on that. It's going to be due next Wednesday. And then remember to start forming your final project groups and writing your final project proposals. The proposals will be due on September 26th in 2 weeks. And we'll have submission instructions for you coming up shortly. So probably towards the end of this week, we'll post instructions for how to submit that. And of course, the project proposal counts the same as any other homework in terms of late days and so on. So do make sure that you get that in. Maybe consider starting to write it early. And it's also important for all of you thinking about final projects, because the project proposal is also an opportunity for you to receive feedback on your project idea and make sure that it's really of the right scope and breadth and so on. All right, today's lecture. Today, we're going to talk about what happens if we basically just have a critic without an actor. So last week we covered actor-critic algorithms. Now we're going to talk about, okay, if you have an actor-critic algorithm and you take out the actor, can you just get by with only a critic? And in many cases, you actually can. We're going to talk about extracting a policy from a value function. So if you have just a value function without a policy, you can get a policy out of it. We're going to cover the Q-learning algorithm. And then these will probably actually do, on Friday, some extensions to the Q-learning algorithm, like continuous actions and various practical improvements. So the goals for today's lecture will be to understand how value functions give rise to policies, understand the Q-learning algorithm, understand some practical considerations, and also maybe some theoretical considerations if we have time towards the end. All right, so to start, let's recap the actor-critic algorithm that we covered last week. So last week we talked about a batch mode and an online version of the actor-critic algorithm, and here I have the batch mode version, but the online version is pretty similar. So the actor-critic algorithm is basically a way to do policy gradients where you can reduce the variance of the policy gradient by using a critic. So just like in policy gradient, you generate some samples by running your policy. And then, unlike policy gradient, you're going to actually estimate a value function, which we refer to as v hat pi, which is going to try to estimate what is the total reward that you will get if you start off in some particular state and then follow the policy. And we talked about different ways of fitting v hat pi, like, for example, regressing onto Monte Carlo returns or using Bootstrap. Then, for every sample that you've collected, you're going to estimate the advantage of the action in that state. So for every sample, you'll estimate a hat pi si ai by using the reward that you actually got, and then the value at the next time step minus the value at the current time step. And this tells you how much better is that action than the average action in that state according to your estimated value function. And then when you go to compute your policy gradient, instead of multiplying grad log pi by the total rewards, you're actually going to multiply them by the advantages, which will give you a lower variance estimator for the policy gradient because this advantage estimator is doing a better job of actually estimating that whole expectation, that whole integral over possible eventual futures, rather than using a single sample. So that was the actor-critic algorithm that we covered last week. But now we could ask this question. If we're going to train one of these critics, and let's say we succeed at training the critic properly, it does what it's supposed to do, can we actually omit the policy gradient entirely? Can we somehow extract a policy right from the critic without having to do anything with the previous policy? So to try to figure out how we might do this, let's go back to the definitions of some of these objects. So we have our advantage function. So our advantage function is a function of state and action that tells us how much better is the action AT than the average action. And average under what? Well, average under the policy pi that you used to fit that advantage function. So that means that if you choose your action by taking the argmax of the advantage function, that's the best action you could possibly take from ST if what you're going to do afterwards is follow pi. Of course, it matters what you do afterwards. If what you do afterwards is like follow a random policy, then AT may not be the best action to take. But if what you're going to do after taking AT is to follow pi, then the argmax of the advantage is the best thing you can possibly do if your advantage estimator is accurate. So that if it's the best that you can possibly do, then it's at least as good as any action that you would sample from your policy. So basically doing this argmax is at least as good and usually better than sampling from the policy if what you're going to do afterwards is follow the policy. And this is true at every single time step, which has an interesting implication. If I take my action according to this argmax, now I land in some state, and in that new state I could choose to follow the policy, and I know that's going to be at least as good as my old policy and probably better because I took the action according to the argmax, or I can do the same thing again. I can do the argmax again, which will again be at least as good as my policy. So if I do the argmax everywhere rather than just at the current time step, that will also be at least as good as my policy, if not better, because it's at least as good, if not better, every single time. And that's regardless of what pi is. So for any distribution pi, if you did a good job of fitting the advantage function for pi, this is true. So then we can say, well, okay, forget policies. Let's just always act like this. Who cares where pi came from? I'm just going to take my actions using the argmax.
Why you can also look at the q only without the
Correct, yes. So the q function is equal to the advantage function up to a state-dependent value.
It's the same argument.
Yes, that's right. Okay, so just to make this concrete, if you change your policy from pi to pi prime, where pi prime takes an action with probability 1 if it's the argmax of the advantage, and probability 0 otherwise, that's just basically formalizing in math what I wrote up here, then pi prime will be at least as good as pi, and oftentimes actually better. Yes?
Can we do this for all time steps simultaneously? Like, do we have to take it step by step, or can we just
Yeah, so,
our policy?
right, so the question was, can you do this at all time steps simultaneously? And the answer is yes. So the reason that I talked through it step by step is just to make the argument that, you know, this is why it's okay to do it everywhere rather than just at a single time. You don't actually have to do it step by step. Obviously, just take your whole policy and just change it up. And it will improve, you know, for the same reason as it did there. Yes, question back there.
Just to be clear, that would give a deterministic policy, right? Because we're following the argmax, that means your action is always the same.
Right. The question was, this gives you a deterministic policy. Yes, so this policy that I wrote down here gives a probability of 1 to some action and 0 to everything else, so it's a deterministic policy. There's actually an interesting fact that maybe might be relevant at some point for some of you, which is that if you have a fully observed MDP, so no partial observation, then there always exists a deterministic policy that is at least as good as the optimal policy. Put another way, in a fully observed MDP, there is in principle no benefit to being stochastic. So there's an optimal policy that is a deterministic policy. There might be benefit to being stochastic while you're learning. You might learn faster, you might explore faster, and we'll talk a lot about that. But in the end, you can always find an optimal deterministic policy. The same is not necessarily true for partially observed MDPs. Okay, so if we're going to try to take advantage of this kind of policy improvement trick where we can use the argmax to get a better policy than what we had before, we can kind of start to sketch out a potential reinforcement learning algorithm that has the same 3 stages, but looks something like this. Maybe in the model fitting stage, it's going to somehow fit an estimate of the advantage, maybe by learning the value function like we did last week, or even by learning the Q function, so something that gives you the advantage. And then in the blue box, where we go to improve the policy, we're not even going to bother with explicit policy gradient. We're just going to set the new policy to be this pi prime. So we'll set pi to be this thing, because that fully determines our new policy. And now we don't even need a specific neural network to represent our policy. We'll just repeatedly do this thing. So this is, in essence, a policy iteration. So a policy iteration essentially does this. It evaluates your current policy. So policy evaluation is what we talked about last week. And evaluate the policy means you're going to estimate a value function or a Q function, but in the end, that's enough for you to get your advantage function. And then you're going to set pi to be pi prime. You're going to set pi to be the best policy, the best policy that you can get directly out of your advantage function, which is what you get with that argmax. So pi prime is just this thing. It's 1 for the argmax and 0 otherwise. and you just repeat this process until convergence. So the second step is pretty straightforward. You just set your policy to this. The question usually is how do you do the first step? How do you do the evaluation? And by the way, we could do evaluation using just Monte Carlo, just like we did last week, but it turns out there are better ways to do it, and if we think through it, we'll actually arrive at some very nice algorithms that are quite practical to use in practice. So let's talk about step one. Let's talk about the evaluation. Just like before, the advantage is given by the reward plus the expectation of the next value minus the current value, so we're all good on that. So what we can do is we can say, well, just like before, let's evaluate vpi. Vpi seems awfully convenient to evaluate. It's a function of just the state rather than the state and the action, and you can use it to recover an advantage, so let's talk about vpi. So what I'll do first is I'll talk about how we can recover vpi in a pretty easy way if we assume that the transition probabilities are known. So this is dynamic programming. And then from there, we'll actually go into a setting where we'll introduce function approximation, we'll introduce sampling, and so on, and get rid of these assumptions. But it's quite illustrative, I think, to first walk through the dynamic programming setting where you assume you know all the transitions everywhere, and furthermore, we'll assume that we can maintain a tabular representation of our value function. So let's just assume that we know P of S prime given S comma A, and that S and A are both discrete, and they're relatively small discrete sets, small enough that we can actually store a table with one number for every state in a computer. In general, this won't be true, but let's just walk through the algorithm and see what it does. So an example of an environment where S and A are both discrete and small, you can have a little grid world. It has 16 states, and you can walk around in those states, so you can basically go left, right, up, and down. 16 states, 4 actions per state. That means you can store vpi of S just as a table with 16 numbers. This is, when you hear someone say tabular representation, what they mean is we're going to store vpi of S as a table of numbers. So that's a table of numbers, 16 numbers. The transition operator is a 16 by 16 by 4 tensor. That gives you the probability of going into each state given the state you were in and the action that you took. So it has 16 times 16 times 4 numbers in it. And you can write down an equation for the bootstrap update for the value function, just like we did last week. You can say that vpi of S, that should just be equal to the expectation under your policy of the reward at of S and A plus gamma times the expected value at the next state. And the reward we know, we just assumed up here that the transition probabilities are known. The policy obviously is fixed for this because we're doing evaluation. So the only thing that we really don't know is what we plug in here. So just like last week, we'll just say, let's plug in the current estimate of the value function. So we have some table. We're going to use that table to evaluate the right-hand side, and then we'll assign that to the table again. So we'll just repeat this process. And then when it comes time to improve our policy, we'll set our new policy pi prime to this. And we can represent our policy as a table too. It's just a table, it's a 16 by 4 table of numbers with a probability for every action in every state. So this will improve our policy, and this will evaluate it. And of course, it's a deterministic policy, right? It's a deterministic policy pi of S equals A, which means that we can simplify this equation up here a little bit because it's an expectation under pi, but pi is deterministic, so what we can do is we can rewrite that equation just by removing all the stuff that has a probability of 0, and then we get this equation, right? So here we just plugged in the deterministic pi instead of A, and we're slightly simplified. So we can do policy iteration with dynamic programming. It's very simple. Step 1, evaluate vpi. Step 2, set pi to be pi prime. Pi prime is this equation that we saw before. And the evaluation, step 1, that's just done by repeatedly applying this equation. So you just apply it over and over and over and over again, and eventually it converges to vpi, and then you can go to step 2 and set pi to be pi prime. Does anyone have any questions about this dynamic programming algorithm? Okay. So if you have a tabular representation, everything is very straightforward. You can actually simplify this method even further. You can have an even simpler dynamic programming algorithm. that reduces from 2 steps to 1 step. And the way that we can do that is we can recognize that, well, this thing is an argmax, and as was mentioned before in a question, an argmax of the advantage function is the same as the argmax of a Q function. And the Q function also happens to tell you the value of that action, not just which action to take. So this is the advantage. The Q function is just this first part without the minus V pi. So that means that the argmax of A pi SDAT is equal to the argmax of Q pi. So that's a little bit simpler. And now, if we think about what the value of that action will be, like how does this process work? Well, you can construct your table of Q values. You can basically take your expected next value and the current reward, and that'll give you a table that's S by A. So if you have 16 states and 4 actions, it's a 16 by 4 table with a Q value in each one. When you compute the argmax, you're basically going to take, for every row in this table, you're going to take the entry with the largest value. That'll tell you which action to take. So the argmax gives you the policy. But the max part actually tells you the value. So if you take the index that gives you which action to take, if you take the number in there, that gives you the value of that action. So what you can do then is you can actually skip the whole policy part and just compute the values directly. So you can estimate the Q function like this, and then instead of trying to recover a policy and plug that policy back into the value function, you can just literally take this number and write that back into your value function table. So now you can write this algorithm in 2 steps, but it's actually a 1-step algorithm. You can estimate this Q function table and then take the max over the for each row, take a max over the columns and write that into your new value function. And you can implement, like if you're implementing this in Python, in NumPy or something, you can implement this in 1 line, right? Because it's just an element-wise max of a 2D array, and the 2D array can be constructed right here. So this is value iteration. In value iteration, you can kind of view that max step as a policy improvement step, but if you're implementing it, you just implement it on 1 line. Question?
When do we stop this process again? Like, exactly.
Yeah. So you can actually show that this process converges. It's a fixed point iteration algorithm. And you can stop it when the infinity norm of the difference between the left-hand side and the right-hand side of this equation is less than some threshold. So formally, you can show that this thing will reduce the infinity norm between the optimal value function and the current value function. So it makes sense then to use the infinity norm as a stopping criterion. Okay. Question?
But now V will not represent value function, like the average. It will now represent the maximum or the...
Right, so the question is, the value function seems to be doing something about the maximum rather than the average. This question is very closely linked to another question, which is, well, okay, it's a value function, but it's a value function of what? Right, before we had V pi, that's the value function for pi. What policy is this a value function for? Well, the answer is that it's still a value function for pi, you're just not representing pi explicitly. And every time you do a policy improvement, this part, when you take the max, what you're really doing is you're writing in the value function for this pi prime defined as this argmax. So as you're improving pi, you're sort of at the same time recomputing its value, which means that at the end, what you're going to get is the value function for the optimal policy. And of course, if you need to recover a policy from it, just use this thing up here. Okay, so far we talked about dynamic programming where we know all the transitions, we have a small number of states and a small number of actions, which are all the things that we don't have in this course. So let's try to figure out how to go from what we discussed so far to an algorithm that we can actually use for complicated large problems. So the first thing we're going to deal with is the representation issue. How do we represent V of S? In a big table where you have 1 entry for each discrete S, everything is very simple, and it's very easy to implement very nice, stable convergent algorithms. So literally for every state, there's a number. But it's very hard to make this method scale to complicated problems. Let's say that I'd like to drive a car. I'm playing this racing game, and I want to do it from images. Each pixel in the image can take on, it has three color channels, each with values between 0 and 255. And it's a 200 by 200 image. So the total number of possible images I might see is 255 to the 3rd power to the 200 times 200 power. And you can plug this into a calculator. It's a very big number. It's more than the number of atoms in the universe, and you will never, ever, ever be able to represent this in a computer. And this is referred to as the curse of dimensionality, which says that if you want to use tabular representations, then the number of entries you need in your table is going to go up exponentially with the number of dimensions in your problem. So here dimensions are each pixel in each pixel's color channel. So the table thing is bad news, of course. So what we want to do is we want to use function approximation. We don't want to have a single entry for every single possible state. We want to somehow train a model that will give us values at different states without having to represent all of them explicitly. So what if we have a neural net function that maps from states to their values, just like we did last week? So again, it's going to take in S, and it's just going to try to spit out V of S. And it's going to have some parameters phi, just like before. So what we can do is we can borrow the same idea from last week and say, well, let's just train it with regression by minimizing mean squared error. And before we would assign the max over Q to the table, now we're going to regress onto the max over Q. So we'll generate some sampled states. For each sampled state, we'll compute the Q function, compute its max, and then we'll solve this regression problem. So now our fitted value iteration algorithm, it will again have two steps. In step one, you're going to evaluate this max Q, and here I just plugged in the definition of Q to make it clear that it really depends on the previous value function. And in step two, you're going to compute the parameters phi that minimize this squared error. So this is referred to as fitted value iteration. It's just like the value iteration we had before, only now instead of just assigning these values, we're going to regress onto them. Now, there's a little bit of a problem with this approach. You can implement this, but it still requires you to know the transition probabilities. Can someone tell me where in this algorithm do I need to use the transition probabilities? Yeah. Right, so the answer was for the expectation over the value. That is true. I could go in and replace the expectation over the value with just the value of a sampled next state, but I actually would still be in trouble. There's actually another place, it's a little subtle, but there's another place here where I really need to know the transition probabilities. Or put it another way, it's something that I can't do if all I'm allowed to do is sample trajectories. As a hint, it requires you to teleport back to a state you've been in before. And try different actions from that state. Yeah. Right, it's the maximization out here. So what does this maximization require you to do? If you want to evaluate the max of this expression, that means that you need to find the value of that expression for different actions. If I have 5 different actions, for every single state I need to evaluate 5 different numbers by trying 5 different actions here. But I can't go back to a state twice and try 2 different actions, except for the first state, right? Because in general, if in a stochastic environment, especially with a very large state space, I might never even visit the same state twice. So this max is actually bad news. So you need to know the outcomes for different actions. And in general, we don't have the ability to acquire that if we don't have a model of the environment. So let's think about how to deal with this. And it turns out that there's actually a pretty easy way to deal with this. It involves a little bit of sleight of hand, but you can actually get rid of this issue. So to figure out how to deal with this, let's go back to policy iteration. So in policy iteration, we can write it like this. You're going to evaluate q pi somehow, and then you're going to set pi to pi prime, where pi prime is the argmax of q. Let's just go with the argmax of q version for simplicity and not worry about advantages for now. Right, so you evaluate q, set pi to be pi prime. So before we were representing the value function with our function approximator. And we were evaluating q by doing policy evaluation and then just using this part to give us the q function. And we're doing policy evaluation by repeatedly applying this, this operator on the value function. So what if instead of trying to fit the value function in this way, what if we instead learn the q function? So the q function is a function now of states and actions, so it's a little harder to represent. But the procedure for getting the q function is not any different. You know, You do have to plug in the pi of s prime here. So before you would plug in pi of s because this was a function of only states, so you plug in pi of s for the action. Now this is a function of states and actions, so you plug in that action here. But then for the next value, you don't have the value function, you have the q function, so you have to plug in pi of s prime for the action at the next time step. So it's a slightly different equation, but very similar principle. And now this equation tells you how to update your q instead of your v. And if you represent q explicitly, either with a table like we did in the dynamic programming case, or with a function approximator with a neural net, if you have q, then doing this argmax does not require trying different actions multiple times. It just requires running different actions through your q function, which is easy to do because in dynamic programming it's just a big table, and if you're doing the fitted version, then it's a neural network. So it doesn't require actually interacting with the environment, it just requires interacting with your q function, which is just stored somewhere in memory. So now you can do the argmax. And then you can fit this thing using samples just like in fitted value iteration. Okay, so that way, now there we had to take a step back to this policy iteration world. Can we do the same kind of max trick that allowed us to go from policy iteration to value iteration to now get q iteration, q value iteration? So remember, what we did before is we went from this algorithm, which evaluates v pi and then explicitly updates pi by setting it to pi prime, to instead have this algorithm that just computes the value of that new policy without actually explicitly representing the new policy, and then just regresses onto those values. So this is the fitted value iteration. And now we'll do the same thing for q values. So we'll forget the policy, just compute the value directly. And we'll do this for the q function in a way that doesn't require us to know the transitions anymore. So the fitted q iteration algorithm, it will compute target values. Now these target values don't have a max in them anymore because they're functions of states and actions. And then we'll regress onto those values. And now our neural net represents a function of states and actions. Now we still need a maximization somewhere, right? That maximization, that's what's actually improving your policy. So before we had a maximization out front, but now that's not there anymore because it's a function of states and actions. So where is our maximization happening? All right, I hear a few hypotheses. Could someone volunteer and state the hypothesis about where the maximization is happening? Yes?
Value function?
The value function, right. So there's this funny symbol here. You know, I said I'm fitting q, but I have a v here. What the heck is that v? I don't have a v, I have a q. So what we're really doing is, instead of this v, what we're going to plug in is a max over the next action of q phi of the next state, comma, the next action. So this thing, this v phi of s prime, that's actually a max. This max doesn't require trying different actions in the simulator or in the real world. It just requires running different actions through our q function to pick the best one. And we just write that in there for that v. So that's where the max lives. So this doesn't require simulation of different actions. It just requires us to use our function approximator, which means that here now we no longer need to be able to simulate different transitions. We just need to be able to generate samples, which puts us back into the world of model-free reinforcement learning. So this algorithm works for off-policy samples. The reason for that is a little subtle, but I'll go into that in a second. So unlike actor critic, which required samples to actually be drawn from your policy, you can actually use samples that you got from other policies to evaluate this. We'll see that shortly. There's only one network, so there's no separate policy. There's only a q phi. There's no high variance policy gradient. We don't have to worry about policy gradients at all here. The downside of this approach is that while it's guaranteed to converge in the tabular case, where you represent your full q function with a big table that states by actions, in the case of function approximation, when you're using, let's say, a neural network to represent the q function, this procedure is actually not guaranteed to converge. And I'll talk about this a little bit more towards the end of today's lecture. Okay, so let's just, this was the derivation. Let's just write out the full algorithm the way that we might actually want to do something like this. And what I'm going to do is on the left side, I'm going to write out steps of the algorithm, and on the right side, I'll write out parameters of that step. Because there's actually an entire family of fitted Q iteration algorithms, and depending on the choice of these parameters, you actually get different methods. So the first thing you need to do, that's the orange box in our standard reinforcement learning algorithm anatomy, is you need to collect data. And the neat thing about Q iteration algorithms is that they don't actually require the data to be collected by your latest policy. There are some formal conditions that the data needs to satisfy, like for example, it has to have the same support as your policy. So if you want to learn how to drive your Jeep in the forest and you only see data driving the Jeep in the city, then obviously that's not going to teach you anything about the forest. So the data needs to have the same support, but you're not actually required to have data that is from the actual policy that you're learning. And what you have to choose when you're collecting the data is how much data to collect, so the data set size n, and how you're going to collect it, the policy that you're going to use. And we'll discuss a few different options there. Then you're going to compute target values. This is very similar to what we did when we trained the critic. You have to go through your entire data set and compute these target values y, which we're going to do now by taking the reward of that transition plus gamma times the max of the Q value at the next state, right? So that's that max that we had on the previous slide. And then we're going to set our phi to be the argmin or the approximate argmin of this mean squared error regression objective. So this could mean just like run SGD to minimize mean squared error to train the parameters of your Q function to regress onto those target values. So you have a Q function, it takes in states and actions, it has parameters phi, and it spits out scalar values. And you have to choose how many gradient steps you're going to use to train it. Sometimes you might take just one gradient step. If you collected a very tiny amount of data, maybe you don't minimize all the way, you just take one step. If you collected a huge amount of data, maybe you want to take more steps. So this is an important choice. And different algorithms are actually different limiting cases of those parameters. And you also repeat this process multiple times. So you could update phi, recompute target values, update phi again. You can do this many, many times, maybe without even collecting any more data. Maybe you can't collect any more data. Maybe your data is just like historical data that you collected years ago and you're just doing fully off-policy learning. Or maybe you're doing something that's very online, in which case maybe k equals 1. So you just go through this process once and then go get more data. So there's choices there. So you have to choose the number of these fitted Q iteration iterations, which is k. And actually on Friday we'll talk about actual deep RL algorithms that have been described in the literature that are all kind of limiting cases of this basic procedure. So this is sort of the high-level recipe, and you can instantiate this recipe with different choices of n, k, and s. Okay, and then of course you repeat this whole process. So does anyone have any questions about the fitted Q iteration algorithm? Yes, back there.
When you go back to step 1 again, after you're done iterating over steps 2 and 3, and you have to collect the data set again, is it dagger style in the sense, are we then going to extract our policy and then use that to?
Right. So the question is, after you've done all this hard work in steps 2 and 3, and you go back to step 1, do you need to like extract a policy from your latest Q function? The answer is it's a choice. So that's basically this choice, the choice of the collection policy. Very, very often, in fact, almost always for fitted Q iteration algorithms, the collection policy depends on the Q that you're learning. I mean, if it didn't, then you could just do step 1 once and collect all your data. Usually it depends on the Q that you're learning, but how it depends on that Q is actually a very delicate choice. And we'll discuss a few options for that choice. We'll discuss some options today, and we'll actually discuss many more options when we talk about exploration towards the end of the course. Okay, so I mentioned before that this procedure is off-policy. Off-policy means that step 1 doesn't have to use the policy pi that's induced by the current Q function. It can use slightly different policies. Why is that? Why is this algorithm off-policy? Well, this algorithm is off-policy because none of the other steps really assume that your data came from any particular distribution. So this thing, this max, is basically evaluating the value of your best possible policy under your current Q function, even for data that didn't come from that thing, because this max just directly gives you that value. So you don't care whether the state S prime actually came from running that policy. You're going to get the value of that policy at that state anyway, provided that your Q function is reasonably accurate. The transition here, the action, it did depend on some policy, but you're not estimating the value function, you're estimating the Q function. So the Q function needs to be estimated for all states and actions, so you don't actually care that this action didn't come from your policy because you're going to have to estimate the Q function for all the actions anyway, not just the actions from your policy. So that's all okay. So this approximates the value of your policy pi prime. The transition is independent of pi given S and A, so you have both S and A, which means that this transition doesn't depend on the particular pi you're using. It's going to transition to the same state no matter what, or the same distribution of states. So neither this step nor this part actually assumes that the data came from any particular policy, which means it's all fine to use off-policy transitions, provided that they have overlapping support. So of course, you might get a very bad estimate of the Q function if your data doesn't actually cover the regions where your policy will go. So you need to have some data in the same regions, but the distribution doesn't have to match. So some intuition for kind of a mental model of how this Q iteration procedure works is you basically have some soup of transitions. Somewhere you got those transitions. Maybe you got them by running your policy and getting trajectories. Maybe you got them some other way. You don't really care. There's just a soup of these transitions of states, actions, and next states. That's going to be your data set, and you're just crunching on that data set to update your Q function. So you're enforcing this relationship, QSA minus Y. You want QSA to be equal to target values for all the transitions in your data set. Okay, then we might ask, well, what is this algorithm actually optimizing? Is it optimizing something, and if so, what is it? That's actually a very delicate question to answer, and for neural network function approximators in particular, the answer is that it's actually not optimizing anything. But for tabular function representation, it is optimizing something, and also step 3 is always optimizing something. So let's talk about step 3 for a second. Step 2 improves the policy, and then step 3 is minimizing something, and it's minimizing what's called the Bellman error. And I'm going to use the script letter E to represent Bellman error. So if you substitute in the equation for this step that improves the policy, the Y, into this squared error, this is the thing that you're actually optimizing. You're optimizing the expectation under the state action distribution in your buffer, which came from some collection policy, of the difference between the left-hand side and the right-hand side of the Bellman equation, where the right-hand side is this stuff, and the left-hand side is the Q value. So that's literally what you're optimizing in step 3. The overall procedure under function approximation is not guaranteed to minimize this quantity, and I'll talk about why that is at the end of today's lecture. In the tabular case, you are actually guaranteed to minimize this quantity. And if the error goes to 0, which it can in the tabular case, then that means that the left-hand side and the right-hand side are equal, which means your Q function is equal to R plus gamma times the max of the next Q value. And you can actually prove, it's actually not too difficult to prove in this case, that the policy that results from that is the optimal policy. So if you use the policy that gives probability of 1 to the argmax and 0 to everything else, and your Q function satisfies this equation, then your policy will be the best policy you can possibly have. That is true if the Bellman error is 0, which you can get in the tabular case. In the function approximator case, then it's a lot harder to say what you're actually going to get. Okay. And sometimes if you see someone write Q star or pi star, Q star basically refers to the Q function that satisfies this equation, and pi star refers to the policy extracted from that Q function, which is the optimal policy. And if someone says, oh, my algorithm learns Q star, that means that they believe that their algorithm learns the Q function that satisfies this equation. Yes?
What is the definition of optimality again here for both Q and pi?
The definition is that it maximizes the reinforcement learning objective, meaning that the expected reward on a pi is as large as it can possibly be for any pi. Question back there?
So does that mean it's guaranteed convergence? Like there's no like local minima or anything?
In the tabular case, yes. In the function approximator case, local minima are the least of your problems. There are much worse problems. Okay, yeah, so most guarantees are lost when we leave the tabular case. Okay, so we'll come back to the theory a little bit later, but now let's talk about some more practical points about this method. So I went through this kind of general full fitted Q iteration algorithm. You can actually, for particular instantiations of n, s, and k, get a version of this algorithm that is fully online, just like we had an online version of ActorCritic last week. So the online Q iteration algorithm is going to look like this. We're going to, in step 1, we'll take just one action, and then we'll observe a transition, Si, Ai, Si prime, which is the state that we landed in, and Ri, which is the reward that we received from taking action Ai in state Si. So that basically amounts to saying n equals 1. You get exactly one transition. In step 2, you'll compute a target value. So you'll compute a target value for that one transition. You have everything you need to compute the target value. You have the reward, which you got right up here. You have your old Q function, which you're going to use to compute the max. And the only thing you need here is the S prime, which you also got up here, because the A prime is what you're maximizing over. So from just that one transition, you can get a target value for that transition. And once you have the target value, then you can compute the gradient of the Bellman error, the gradient between your Q value at that state and the target value you just computed. You compute that gradient with respect to the parameters of your Q function phi, and then take a step in the direction of that gradient. So here, we chose to collect n equals 1 transition, take s equals 1 gradient steps, and go through this loop k equals 1 times. So everything is 1, and that gives us a fully online algorithm. In reality, this algorithm can work well for tabular representations or very, very simple function approximators like linear functions. It will not work very well for neural networks. And we'll talk about some practical improvements probably on Friday about how to instantiate this with deep neural network function approximators. There's a few things that you need to stabilize training in those cases. And of course, step 1 is still off policy, so you can take that action using a variety of different policies. This is actually, this online Q-learning algorithm, this is the classic Q-learning algorithm. So if you ever hear of Watkins Q-learning, this is what this is referring to. Okay, so let's talk about that off-policy thing, the policy that we can use to execute step 1. There are a number of different choices, and the most obvious choice might be to just use the best policy that you have. Like if you have a policy, you think it's good, why not just use that to collect this transition? So your policy, your final policy, once you've learned your Q function, will be given by probabilities 1 for the argmax and 0 otherwise. So if you have a guess at the current Q function, maybe you're not done learning yet, but that's as good as you've got so far, perhaps you can use the best policy for your Q function. Can someone tell me why this is not a good idea? Why might we not want to use this policy in step 1? It needs to explore? Can someone tell me what that means?
Like you want to make your policies such a way that you haven't explored states enough, so you want to maybe explore other spaces that your policy doesn't cover.
Right. There was another suggestion back there?
Yeah, so it's deterministic, just like each time you're just going to do the same thing.
Right. Okay, so the two answers were, well, maybe there's some states that you haven't been to yet, and perhaps you might want to go there, and this thing is deterministic, so it'll just do the same thing over and over again. And that's basically the crux of the issue, that this is a deterministic policy. It's greedily trying to do the thing that it thinks is best, which might cause it not to visit some states. In fact, it will very likely cause it to simply ignore some parts of the state space. And maybe those parts of the state space are really good. Maybe you're over here in the world where your rewards are all kind of 0, and there's a big pot of gold over in that corner of the room that you just haven't visited yet. So if you just stay over here, maybe I've learned that, well, if I just sit down in the chair, I won't get tired and I'll be kind of happy, but I'll never reach that pot of gold. So if I explore, if I do some things that I think are actually suboptimal, maybe standing up from the chair and walking over there, it's a little bit of exercise, makes me a little tired, but I might find the pot of gold. So sometimes taking the thing that is not optimal when you're learning might actually be desirable because it might lead you to figure out what is more optimal later on. There was a question in the back? No, okay, just stretching your arm, okay. Okay, so why is it a bad idea for step 1? Well, because you need to explore. All right, so how do you explore? Well, what else can you do other than this policy, this deterministic policy? A very, very simple choice, and one that tends to work decently well for relatively simple problems, is to do what is called epsilon greedy exploration. Epsilon greedy simply means that usually you're greedy, usually you do this. This is referred to as the greedy strategy. Do the thing that you think is best so far, but with some probability of epsilon, you might do something else. And it's not a very intelligent strategy. It just says with probability of epsilon, just do something else, do anything else. So it just says that with probability of 1 minus epsilon, you take the argmax, and with probability of epsilon divided by the number of remaining actions, you take one of the remaining actions. So uniformly at random, you'll do something else. Doesn't matter what, just something random. So that's the epsilon greedy strategy. Why is this a thing? There isn't any reason for it to be especially good, but it works decently well in practice, and it's really, really simple to implement. So very, very often, if you have a discrete action problem where this actually makes sense, using an epsilon greedy strategy is a good choice because you can code it up in 5 seconds, and it's often actually good enough. There is a more nuanced choice, and we'll actually discuss some of the theoretical backing for this choice later in the course, which is that maybe you don't want to take all actions at random with equal probability. Maybe the intuition is that you believe that some actions are good and some are bad, and some are about kind of in the middle. The actions that you're pretty sure are terrible, just don't take them. Like if you think this action is going to make you like die a horrible death and it has like a really negative reward, just don't go there. You don't need to explore that anymore. But if you have a bunch of actions that are all about equally good, then maybe it's worth choosing randomly between them. And one way to formalize this notion is to do what's called Boltzmann exploration, where the probability of taking an action depends on its Q value. You can use a variety of different positive transformations of Q values. If you exponentiate the Q values, that amounts to saying that really low Q values, you just never want to take those actions. And if you have multiple actions that are about tied, then you should take them about equally at random. And what people often do is they'll do Boltzmann exploration, and they'll put a multiplier in front of the Q, which acts as a temperature. So if you multiply the Q's by 0, then you take all the actions completely at random. If you multiply it by like 0.0001, it's almost random, but slightly biased towards better actions. If you multiply them by 1,000, then you'll almost always be taking the greedy action. So that temperature essentially controls how much you explore. Boltzmann exploration can be a good choice. It can be a good choice for continuous action problems, and as we'll learn later on in the course, there is actually a variant of reinforcement learning that justifies why in some cases Boltzmann exploration could actually be a very good thing to do, but it requires a slight modification to the standard framework of RL. So maybe from a practical standpoint, what I would say is that if you have a discrete action problem, which is usually where you would be using this Q-learning algorithm anyway, epsilon greedy is a very good place to start, and it's a fairly well understood method that people kind of know how to tune it. Boltzmann exploration has some interesting properties. In practice, for discrete action problems, if you just do it kind of naively, it's not really going to beat epsilon greedy necessarily, but if you do a few things very carefully and just right, it might have some interesting properties for your problem, and we'll talk about that more later on in the course. There are many other ways to explore. Many of them are much more sophisticated than simply randomizing the policy. Many of them are more goal-directed, and we'll actually have an entire lecture on exploration later on in the class. Okay. So let's review what we covered so far. We talked about value-based methods, which don't learn a policy explicitly. They don't have those parameters theta. They just learn a value function or a Q function. And if we have a value function, we can basically recover a policy from that value function by taking the action with probability 1, which maximizes the value. We talked about fit-a-Q iteration, which lets us get away from knowing the transition probabilities. It's a batch mode off-policy method. It doesn't even require the data to be taken with the latest policy. And we talked about Q-learning, which is an online instantiation of that. So it's basically an online version of fit-a-Q iteration. Okay, so at this point, we're going to take a 3-minute break. And after the break, I'll go into a little bit of the theory some more. So we'll be back at 10:59.
When you explore more and more that's variance, how do we fix or pay for it? Or?
Yeah, I get the question. It's a complex question, though. In fact, there's not a heck of a lot of good analysis of how the data distribution actually influences Q-learning. The analysis, to my knowledge, is only about as deep as saying okay, the support has to overlap, which means that if you're trying to find the treasure and you don't have the transition that finds the treasure, you won't be able to find it. But as far as the details of is one distribution better than another, there isn't much analysis. And I think partly why there's so little analysis, because just showing convergence of Q-learning is hard enough as it is under function approximation, that trying to study how fast, if you don't know if it'll even converge, how can you even say, well, it converge faster or slower? So that's probably why there's not as much analysis there. In the tabular case, there's a lot more analysis, but it's also not clear how much the tabular analysis extends to the function approximation case, because even convergence doesn't hold.
I see.
So I guess the real answer is that the study of this stuff is sort of, in some sense, is not so far along to even get to those questions.
I I see, I see. And are there any cases where we subtract the baseline or something here to make it like, we don't want the ones that are, like, we want to go, to go lower?
Yeah, that's an interesting question. One thing that people have looked at is not baselines, but some variant of importance sampling. So there is a little bit of work on importance sampling in Q-learning that just does things like, well, it actually sometimes diametrically opposed. Like sometimes you'll say, well, let's throw out the samples that look like we'll never see them under the current policy. And some others say, well, let's actually throw out the samples that we've already learned everything about and just keep the weird samples because those are sort of the hard negatives. And ironically, both of those can help in some cases, even though they seem like they're opposed. So a lot of this work is more empirical, but if you look up something like prioritized experience replay, that's sort of the hard negative version that says, let's pull out the transitions that we're doing worse on, that we have high Bellman error on. And then importance sampling is sort of the opposite, of saying, well, let's pull out the transitions that seem to have high probability under the policy, because those are the ones that we'll actually see. But yeah, if you're interested in this question, it could be a great topic to study for a final project because we know so little there.
Quick question. So when we say this guarantee to converge, that's about discrete state and discrete action. If it's only discrete actions, you recommend using the epsilon greedy exploration.
Yes. Well, so the convergence is not just for discrete state and discrete actions, it's actually for tabular representations. So not.
How is that different from discrete state and discrete?
Well, you can have discrete state and discrete action, but still use a neural network. So it's not about how many of them there are. It's about how you represent the value function.
Okay.
And I'll actually talk about that after the break a little more.
Okay.
All right, we're going to resume. So in the second half of today's lecture, I'm going to talk about a little bit of value function learning theory. And this is going to be a very pessimistic part of the lecture. It's going to have a very, very sad conclusions, and it's basically, we're going to conclude that everything is horrible in the world. But that's okay, because on Friday we'll have a more upbeat lecture where we'll talk about how, even though there are no guarantees in life, we can still make these things work. So this is going to be a little sad, but then on Friday it's going to be a little happier. So let's talk a little bit about value function learning. So remember this value iteration algorithm, the dynamic programming algorithm that I talked about at the beginning of the lecture. You're going to compute your Q values by taking the reward plus the expectation of the next value. And then you're going to take the max over the actions, and that's going to give you your new value function. So this is the version where you learn a value function. You learn a value function, and you don't explicitly represent the policy. You just use this little max trick to skip that step. That's value iteration. So I talked about how you can do value iteration in tabular environments where you have a table with one number for every single state, and everything is good there. So value iteration does converge, and we're going to introduce a few mathematical tools that help us understand why it converges. I won't actually present the full proof here, but I'll present kind of the tools that we need to construct that proof. The proof is just a bit of algebra. Okay, and then we need to show that it converges, and if it does converge, we need to actually know that it converges to something good. Like you can have algorithms that converge but converge to bad answers. We want it to converge to a good answer. So a very useful tool for analyzing convergence of these kinds of algorithms is to write down what they're doing in terms of some operator. And the operator that we're going to need here is B, which stands for Bellman backup. So the Bellman backup operator is an operator that you can apply to a value function that's going to take your value function, it's going to multiply it by the transition function, by the transition operator, multiply it by a discount, and add the reward. So let me explain the notation here a little bit, because this is for a tabular setting, so everything is vectors and matrices. RA is just a vector of all the rewards for every state and every action. So how you represent it? Well, you can represent it as a matrix where the first dimension is state and the second dimension is action. So you can say it's an S by A matrix. This thing, this TA, the notation here is a little messy because this has to be a tensor multiplication. But this is a matrix of, if I have TA, that's a matrix of transitions for action A, where basically the entry TA, comma I, comma J is the probability of going to state I, given that you were in state J and took action A. So if you construct the matrix TA, TA is a matrix now because we chose a single action, then you can multiply the value function by that matrix, and you'll basically get the backup of that value function for that action. So we'll do that for every action. We'll add the vector of rewards for that action. We'll stack all those things into a matrix, so that we have one column for every possible action we could take, and then we'll take an element-wise max. So for every row in that matrix, we'll do a max over the columns. And that'll give us the backup. So this backup operator, B times V, is just defined as this operation. Does everybody understand the Bellman backup operator? Any questions about it? Okay, good. So this is the only bit of fanciness here, actually. And then what you can show is that the optimal value function, V star, is a fixed point of B. What does it mean for it to be a fixed point of B? It means that if you apply B to it, you get the same thing back. So V star, the optimal value function, is just the value function for which V star is equal to the max over A of R plus the expectation of the next V. This thing is exactly the Bellman operator, the Bellman backup operator, so V star is equal to B times V star. And you can show that if you have V star and it satisfies this equation, if you extract the policy, that policy is the optimal policy. The fixed point always exists, it's always unique, and it always corresponds to the optimal policy. I'm not going to prove that here, but it's actually pretty straightforward to show that. And then the question that we usually have is, will we reach it? So V star is a fixed point of this thing. Can we actually reach that fixed point? In particular, if we start with any old V, and we repeatedly apply the operator B, if we always said V is equal to B times V, do we eventually get to V star? So V star is a fixed point of B, which means that V star is equal to B times V star. And the way that we can prove that value iteration actually reaches V star is by proving that B is a contraction. So what does it mean for B to be a contraction? It means that if you have any two value functions, V and V bar, and remember that value functions here are just vectors. They're just vectors of numbers with a number for every state. You have two vectors, V and V bar. B is a contraction if and only if BV minus BV bar under some norm is less than or equal to some number less than 1 times V minus V bar under the same norm. So basically, if you apply B to both V and V bar get closer together. Hence the word contraction. So you're contracting the distance between these two things. And you can actually show that the Bellman backup operator is a contraction, but the details here matter. It's a contraction with a multiplier of gamma, which is kind of neat. That's the discount. It's less than 1. And under the infinity norm. Under the infinity norm means that the largest difference between the entry with the largest difference in V and V bar is going to become smaller. How much smaller? Well, by at least gamma. The proof is not actually terribly interesting. It's just a bit of annoying algebra, but it takes about a page, so I'm not going to write it out here. So if you're interested in the proof, post on Piazza, we can link you a document with a proof for it. But the important bit, contraction under infinity norm. Gap always gets smaller by gamma. So now, how do we use this to show that you will actually reach V star? Well, the way that you show that you will reach V star is to choose V bar to be V star. So if V bar is V star, then B times V star is equal to V star. So if I substitute in V star for V bar, then this bit just becomes equal to V star. So that means that if B is a contraction, then B times V minus V star under the infinity norm is less than or equal to gamma times V minus V star under the infinity norm, which means that each time I apply B to my value function, it gets closer to V star. V star doesn't get closer to itself because it's a fixed point, it just stays where it is, but V gets closer to it. So if I start off over here and my V star is over here, value iteration will gradually get me there. So that's good. Value iteration converges. What does it converge to? It converges to the fixed point, the unique, the one and only wonderful fixed point, which is V star, which gets you the optimal policy. Okay, so what happens in the non-tabular setting? Why is it that things are so sad when you don't have a tabular representation? So now that we introduced the Bellman backup operator B, value iteration is very easy to write. You write it on one line. V goes to B times V. That's super simple. Now, what was the fitted value iteration? The fitted value iteration algorithm actually had two steps. It had a Bellman backup step where we compute these target values. And this thing, you'll now, when looking at it, you'll immediately recognize the Bellman backup operator. This is just the Bellman backup operator applied to V. But then, of course, we don't set V to be BV. We have to do a regression problem. And that's what we're doing in step 2. So what is a regression problem? How can we abstractly represent this step 2 with an operator? What does the step 2 actually do? Well, one way that we can abstractly represent step 2 is we can say it's doing learning, and learning means that you have a space of hypotheses and you're trying to find the best hypothesis in your space. So let's say that your space of hypotheses is omega. Maybe omega is the set of all neural networks. You're going to find the hypothesis, or maybe the set of all neural networks with 100 hidden units and 2 layers or something. And you're going to find the best hypothesis in that space, best according to what cost? Well, the squared error. So you're going to find the hypothesis in the set omega that minimizes the difference between the left-hand side and the right-hand side, the difference between the value function that's given by this hypothesis, the v prime, and the backed up previous value function. So omega is maybe like the set of all value functions that you can represent with your function approximator. B times v is your backed up value function. So graphically, we can imagine that these 2 steps do the following. Let's say that this blue dot, this is your current value function, represented by your current neural network. The line represents the set omega. So this is the set of all value functions you can represent with your function class. Maybe the set of all value functions that can be represented with neural networks with 1 hidden layer and 100 units. And I realize that set is not one-dimensional, but just for the sake of illustration, imagine this line is that set, and the whole space, the whole rest of the slide, is a set of all possible value functions. Not all value functions can be represented with a neural network with 1 hidden layer and 100 hidden units. So there are a lot more white stuff than blue stuff. When you apply the Bellman backup operator, when you take v and you hit it with b, when you get bv, that might not lie on this set. So when you compute these target values, those target values may not be exactly representable with a neural network with 1 hidden layer and 100 units. So in general, they will be off of this line. Now, what do you know about b? You know that b is a contraction in the infinity norm, which means that when you take v and you apply b to it, you get closer to v star in terms of the infinity norm. But you might get lifted off of this manifold of functions that you can represent. Now, the learning step, this argmin over here, it's going to bring you back down to the set of functions you can represent. It's going to find some other v prime, which is on this line. It can be represented by a neural net. And in some sense, hopefully, it's actually close to bv. In what sense is it close to bv? Can anybody tell me what kind of distance between bv is being minimized when you find v prime? Yes, the norm. What kind of norm? L2 norm. The L2 norm. Well, yeah, because it's the L2 norm right here. Right? This is what you're minimizing. So v prime is the point in omega that is the closest to bv in terms of the L2 norm. Of course, this is assuming everything is convex. In reality, if it's not convex, maybe it's even worse. But let's assume everything is convex, even though it isn't. In the best case, you're getting as close as possible in terms of the L2 norm. So you can actually define a new operator pi, which is the operator that takes some value function v, which is going to be bv for us, and it finds another value function v prime, which is in the set omega, and it's as close as possible in terms of the L2 norm. So pi is a projection onto omega in terms of the L2 norm. Projection means you find the closest point in the set. So now you can write down fitted value iteration also in one line. You just say v becomes pi b v. So b means backup, do the Bellman backup, and pi means project onto the set of neural networks. So not only is it on one line, it actually ends up being only 5 characters. Shortest algorithm ever. If only it were that simple. OK, so now let's try to see what this algorithm is doing. Like, b is a contraction with respect to the infinity norm. That's pretty good. That means that we're getting closer to v star in terms of the infinity norm. So in particular, that means that bv minus bv bar under the infinity norm is less than or equal to gamma times v minus v bar under the infinity norm. Pi is actually also a contraction. It's a contraction with respect to the L2 norm. That seems like it's pretty good news. Why is pi a contraction with respect to the L2 norm? Well, it's actually very simple. If you imagine a line and 2 different points, if you project both points onto the line, they'll never get further apart. They'll only get closer. So L2 projection, always a contraction in the L2 norm. So far, so good. We have a contraction here, we have a contraction here. We put the two together, and we don't actually get anything because they're under different norms. And that's actually really, really important. So it turns out that if you have a contraction in the infinity norm and a contraction in the L2 norm, if you compose them, you don't get anything. It's not a contraction of any kind in general. And you can kind of visually see how this works. So, you know, if everything is a nice contraction, you get closer and closer to the star. In the case of this projected Bellman operator, the Bellman step gets you closer to the star in terms of infinity norm. So here you can see I definitely got closer, right? Very clearly got closer. Now I'm going to project back down to the line. When you project onto a line, right, it has to be at a right angle, so you know where the projection is. It's right here. And this point can actually be further from V star. So if you do an infinity norm contraction followed by an L2 contraction, you can actually move further away from the optimum. And that will happen. So the conclusion from this, value iteration converges in the tabular case. Fitted value iteration does not converge. It does not converge in general. It does not converge in practice. It will move further and further away from the optimum, and things are bad and sad and horrible. What about fitted Q iteration? Well, we can go through the whole exercise that we went through before for fitted Q iteration also. So for fitted Q iteration, we define a slightly different Bellman backup operator. For Q iteration, the Bellman backup operator is now on Q, so it's given by R, which is actually now a state by action matrix, plus gamma times the transition operator times the max of the Q at the next step. So now the Bellman backup operates on matrices rather than vectors, but same basic principle, just for Q iteration. So the max is now after the transition operator rather than before. We can define the same projection operator for fitted Q iteration. The projection operator just finds a hypothesis Q prime in the set of omega that is close to some target Q. And we can define our fitted Q iteration algorithm just like before. Q becomes pi BQ. It's just the operators are a little different. And we can actually show all the same properties if we wanted to. We could show that the Bellman backup for Q's is also a contraction with respect to the infinity norm. Pi is still a contraction in the L2 norm, and their composition is still not a contraction of any kind. And this applies to online Q learning, batch Q learning, and so on. So now, you know, some of you that are more optimistically minded might say, well, but maybe it's not so bad. Like maybe it still kind of works because it's just doing regression. There's a gradient operator and you're doing gradient descent. So gradient descent converges, right? Shouldn't that be enough for a convergence result? The trouble is that Q learning is not actually doing gradient descent. It has something that looks like a gradient inside of it, but it's not doing gradient descent on a particular objective. Why? Well, because if you actually plug in the y in here into the thing that you're computing the gradient of, the expression that you actually use for the gradient is the derivative of the Q value at some state in action of Q minus the target value, minus R plus gamma max of the next Q. This value depends on your parameters, but you're not accounting for the gradient of that value. So this is not actually the gradient of the Bellman error. This is the gradient of the Bellman error when you pretend that y is a constant. You could also say, well, why pretend that y is a constant? Why not compute a gradient through this thing? Okay, the max is kind of non-differentiable. That's not actually the main problem. You can actually compute the gradient through the right-hand value. You can do all sorts of tricks to soften the max. But then you get an algorithm that's even worse. You actually do get an algorithm that is convergent, but it ends up having really, really, really terrible conditioning and does not work. If we have some time, I might actually cover this later in the course, but this is sometimes referred to as Bellman residual minimization. Bellman residual minimization is very, very difficult. Generally doesn't work. So that's why we ignore the gradient through the y. Okay, there's also another, some bad news so far, even worse news. There's another sad corollary to what I just discussed. And that's going to come back to the batch actor critic algorithm. So we had this nice batch actor critic algorithm that we derived happily last week, which fits value functions and does the policy gradient. Turns out the bad news applies also to the batch actor critic algorithm. So the batch actor critic algorithm with the bootstrap, when you set the y's to be r plus the next v, and then regress onto them, same problem. This r plus the next v, it's a contraction onto v pi in the infinity norm. This thing is a contraction on the L2 norm. So together, they actually also don't in general move you closer to v pi. So L infinity contraction, but without the max. It's a slightly different operator, but similar principle. This is L2 contraction. Together, they still don't get you closer to v pi. So fitted bootstrap policy evaluation also doesn't converge in the function approximator case. I should say that if you do Monte Carlo, if your y is a sum of rewards, then you're actually fine. But if you do the bootstrap version, in general, it doesn't converge. Question?
The problem with gradient descent that you said also applies here, right?
Yeah. So an aside on terminology, just to make sure that we're clear on everything. When I say v pi, I mean the value function for the policy pi. This is what the critic does. When I say v star, this is the value function for the optimal policy pi star, and that's what we're trying to find in value iteration. So if you ever see those terms, that's what they mean. But yeah, this add corollary, bootstrap actor critic, which seems so nice and elegant, also doesn't converge. Okay, so just to review, we talked about a little bit of theory for value iteration. We talked about the operator for the Bellman backup, the operator for the projection, how the backup is actually a contraction in the infinity norm. Value iteration converges because of that. But then when we have function approximation, we have this projection operator. The projection operator is also a contraction, but in a different norm. So the projection plus the backup is not a contraction in anything, and fitted value iteration does not in general converge. For Q-learning, same deal. Q-learning, fitted Q-iteration, etc. with function approximation does not in general converge. But we can make them work in practice. So that was the sad news. Now the good news is that we can make them work in practice. And on Friday, we'll talk about how to make them work in practice. And all of you will actually make them work in practice for homework 3, because that's what the homework is going to be on. So see you all on Friday for the good news.
Can I ask what the number